Welcome to G Fun Facts Online. Today we are talking about a ghost in the machine, a discovery so profound that it is forcing physicists to rewrite the textbooks we have used for a century. We are diving deep into altermagnetism. This is not just a minor tweak to our understanding of materials. It is a fundamental third state of magnetism that breaks the binary duality we have lived with for thousands of years. For all of human history, up until very recently, we believed there were only two main players in the magnetic world. First, you have ferromagnetism. This is the loud extrovert of the magnetic family. It is what holds your grocery list to the fridge and what points north on a compass. In a ferromagnet, like iron or cobalt, the electron spins, which you can think of as tiny internal compass needles, all line up parallel to each other. This creates a strong, macroscopic magnetic field. This is incredibly useful because we can control those spins with external fields, which is the basis for how we store data on hard drives. Spin up is a 1, spin down is a 0, but ferromagnets have a flaw. They are messy. They produce stray magnetic fields that interfere with neighboring components, which limits how small we can pack them on a chip. They are also relatively slow, operating in the gigahertz range. Then we have the second player, antiferromagnetism. This is the silent introvert. In materials like hematite or chromium, the electron spins are perfectly ordered, but they alternate. One points up, the next points down, and so on. They cancel each other out perfectly. To the outside world, an antiferromagnet looks like it has no magnetism at all. It won't stick to your fridge. For decades, engineers called these materials interesting but useless. They are incredibly fast, operating at terahertz speeds, which is 1,000 times faster than ferromagnets. And they are very stable because they have no stray fields. But because the spins cancel out, we couldn't easily read or write information to them. The data was locked away. So for 100 years, this was the law of physics. You could have a material with a net magnetic field that was easy to read but slow and messy. Or you could have a material with no magnetic field that was fast and stable but unreadable. You could not have both. But nature was hiding a third option in plain sight. Enter altermagnetism. Discovered theoretically in 2019 and experimentally confirmed in 2024, this is the Goldilocks phase. It combines the best of both worlds. It has zero net magnetization, just like an antiferromagnet, meaning it has no stray fields and operates at blistering terahertz speeds. But, and this is the game changer, it exhibits strong spin splitting, just like a ferromagnet. This means we can read and write data to it using electric currents. It is safe, fast, dense, and useful. So how is this physically possible? How can something have no magnetic field but still act like a magnet for electrons? The answer lies in the geometry of the crystal lattice. This is where we have to get a little technical, but it is fascinating. In a standard antiferromagnet, the crystal symmetry is simple. If you take a spin-up atom and slide it over to the position of a spin-down atom, the environment looks identical, just with the spin flipped. This symmetry cancels everything out. But in an altermagnet, the atoms are arranged differently. You cannot just slide an atom over to match its neighbor. You have to slide it and rotate it. Imagine a crystal, where the spin-up atoms sit in a cage of other atoms shaped like a horizontal rectangle, while the spin-down atoms sit in a vertical rectangle. If you just slide the atom, the cage doesn't fit. You have to rotate it 90 degrees. This subtle property is called crystal rotation symmetry. This rotation breaks the symmetry in what physicists call momentum space. In a normal magnet, the energy levels for spin-up and spin-down electrons are usually uniform. But in an altermagnet, the spin splitting depends on the direction the electron is moving. If an electron moves north, spin-up might be lower energy. If it moves east, spin-down might be lower energy. This creates a pattern in momentum space that looks like a cloverleaf, or a D-wave. If you sum up all the electrons in all directions, the total magnetization is 0, because the north cancels the east. But, and this is the genius part, if you send a current flowing only north, you get a massive spin-polarized current. It hides its magnetism globally but reveals it locally to a moving electron. It is a hidden order that we have finally unlocked. The timeline of this discovery is incredibly fast. The concept really began to crystallize around 2019. Researchers like Libor Smejkal and Gyro Sinova were investigating anomalies in materials like ruthenium dioxide. These materials were acting strangely. They showed Hall effects, which are usually the signature of ferromagnets, despite having no magnetic field. Using a new mathematical framework called spin group theory, they predicted this wasn't just a weird antiferromagnet, but a completely new phase of matter. They coined the term altermagnetism. Then the race was on to prove it. The smoking gun came in early 2024. A collaboration involving the University of Nottingham and the Czech Academy of Sciences went to the Max IV synchrotron in Sweden. They shone intense X-rays onto a material called manganese telluride. They mapped the electronic structure and found exactly what the theorists predicted. They saw a massive spin splitting of the energy bands, despite the material having zero net magnetization. At the same time, other groups confirmed similar behavior in ruthenium dioxide and chromium antimonide. The third state was real. One of the best parts of this discovery is that altermagnetism doesn't require exotic, toxic, or rare earth elements. It exists in simple, abundant compounds. Manganese telluride, the poster child of this movement, is a semiconductor we have known about for decades. The fact that altermagnetism exists in manganese telluride means it is already compatible with existing semiconductor manufacturing. Then there is ruthenium dioxide, a common conductor used in resistors. We used to think it was non-magnetic, then we thought it was antiferromagnetic, and now we know it is a D-wave altermagnet with a massive spin splitting of over 1.4 electron volts. That is huge. It creates a very potent spin current. We also have chromium antimonide, which stays magnetic at very high temperatures, over 400 degrees Celsius, making it a workhorse for industrial applications that generate a lot of heat. Theorists have now identified over 200 candidate materials, ranging from insulators to superconductors. This abundance means engineers aren't stuck with one difficult material. They can choose the perfect altermagnet for the job. Now, let's talk about why this matters to you. This solves the grand challenge of spintronics. Spintronics aims to use the electron's spin, rather than its charge, to process information. This promises devices that generate less heat and use less power. Altermagnets offer the holy grail combination. First, terahertz speed. Because their internal dynamics are driven by strong exchange interactions, they can switch states in picoseconds. That is trillionths of a second. This opens the door to processors running 1,000 times faster than the chips in your computer right now. Second, high density. With zero net magnetization, bits can be packed atom to atom without erasing each other. We could see hard drives and magnetic RAM with densities far exceeding current limits. Third, easy readout. Because of that unique crystal rotation symmetry, we see something called the crystal Hall effect. The crystal structure itself deflects spin-up and spin-down electrons in opposite directions, even without an external magnetic field. This allows for direct electrical reading of the magnetic state. But the future of altermagnetism goes beyond just faster hard drives. It is a key enabler for neuromorphic computing. Traditional computers, separate processing, and memory. The brain does both in the same place. Altermagnets are uniquely suited to mimic this. Unlike ferromagnets which snap between 0 and 1, altermagnetic domains can be manipulated to store continuous analog values, much like the varying strength of a biological synapse. Their ultra-fast dynamics allow for the generation of nanospikes that mimic neurons, but at speeds millions of times faster than biological tissue. And because they don't produce stray fields, they are energy efficient enough to scale up to the billions of neurons needed for artificial general intelligence. Then there is the most scientifically profound application, quantum computing. We all know that qubits are fragile. Magnetic fields usually destroy the superconductivity needed for many quantum systems. But because altermagnets have zero net magnetization, they don't destroy superconductivity. You can place them directly in contact with superconductors. When you layer an altermagnet with a superconductor and a topological insulator, you create the conditions to host Majorana zero modes. These are exotic particles that are their own antiparticles. They are topologically protected, meaning they are immune to local noise and errors. This is the path to fault-tolerant quantum computing. Recent papers in late 2024 and 2025 have proposed specific heterostructures that could allow us to braid these Majorana modes, performing quantum calculations that are physically impossible to error. Some physicists even believe altermagnetism might be the missing link that explains high-temperature superconductivity in cuprates. It provides a new type of magnetic fluctuation that could glue electrons together in unconventional ways. Of course, we are still in the early days. There are challenges. Altermagnetism depends strictly on perfect crystal symmetry. If the crystal has defects, the effect vanishes. Growing perfect, defect-free thin films on silicon chips is a major engineering hurdle currently being tackled by big fabricators. We also need to master domain control, ensuring we can switch the entire bit reliably billions of times a second without degrading the material. And we need to amplify the signal strength for detection. But the economic outlook is massive. The spintronics market is projected to grow to nearly $30 billion by 2030, and altermagnetism could make that valuation skyrocket. We are looking at a post-silicon logic, where magnetic states do the computing, drastically reducing the world's energy consumption. To conclude, the discovery of altermagnetism is a humbling reminder that nature still holds secrets in its simplest materials. For a century, we looked at manganese telluride and saw a boring rock. We were looking at a Ferrari and calling it a stone, because we didn't know how to turn on the engine. Altermagnetism is that engine. It is the third state, bridging the gap between the static stability of the stone and the dynamic utility of the magnet. From memory chips that hold libraries of data in a grain of sand, to processors that think like brains at the speed of light, the altermagnetic revolution is here. The electrons are spinning a new story, and for the first time, we know how to read it. Thanks for listening to G Fun Facts Online.